We love calculus. We love matrix algebra. So let's bring calculus and matrix algebra together and see what kind of fun we can have. So first of all, we're going to come up with some rules of derivatives. So for rule number one, what we have is a cross, a sum product. So we have a row of x's times a column of a's coefficients. And for example, we might have something like that. And so what we're going to do here is, basically take the gradient of y. So we take y with respect to x1, with respect to x2, and with respect to x3. And so it's a, b, a1, a2, and a3. So the derivative of y with respect to vector, make it bold, vector x, wow, that's too bold, isn't it? Equals a. All right, so the derivative of this with respect to vector x is going to be the a column matrix or column vector. All right, so if we have, I'm not going to show this, but if we have the derivative of x prime a with respect to vector x is going to be a. So if we have the derivative of ax with respect to x, this ends up being a, well, not negative, but the transpose of a. All right, so you can look through the notes on page 36 in the calculus and matrix review and kind of get it right in your head. All right, so if we have the derivative of some sort of quadratic expression, so if we have the derivative of a row vector times a matrix times a square matrix times a column vector, the derivative of that is going to be ax plus a prime x. But if this A is like a covariance matrix, it means it's symmetrical. And if it's symmetrical, the covariance matrix equals its transpose, not the inverse, but the transpose. And so what we end up with is this relationship right here. So it's kind of the multivariate equivalent of taking a derivative. So if we have y equals 4x squared dy dx, bring down to 2, it'll be 8x. So it's the matrix equivalent of that. So we're going to go through this just to show you how much fun you can have. So let's say we had our previous problem. So we have a case where we have a mean variance. So this is the expected return on a portfolio of two risky assets and a risk-free asset. And here is the variance of the returns on the risky portfolio. And let's see how we can write this. So we can write this as a scalar times a row vector, W1, W2. Well, so the transpose of that's a row of W1, W2 times excess returns. So we've expressed this. And minus 1/2 A times, wow, this is the way we can express our variance of the portfolio. A row vector of, so it's going to be W1, W2 times the covariance matrix times W, wow, what is that? Sorry. W1, W2. All right, so this is how we wrote that out. And the exposure of whatever we have in a risk-free rate doesn't contribute anything to variance. All right, so by rule one, we take the derivative of utility with respect to the 2x1 matrix of W. So here we have our variable times constants. And so by rule one, we get a column vector of the excess returns. And by rule 3, this is going to be 1/2 times the covariance matrix times W. And so the 2's cancel out. And so we get our first order condition. Oh, I guess we can set that equal to a 2x1 vector of zeros. All right, so bring this over to the other side, divide through by the scalar A, the risk aversion coefficient, take the inverse, the left-hand inverse, and we get the same equation. So it's pretty cool. All right, so let's now look at the second order condition. Let's find a Hessian. So we take our first order condition, this thing in the gold, with respect to W. So the W is only where there's a blue. All right, so we got this negative A times the covariance matrix. And so we saw that equals, that is a negative definite. And so, yay, it works. All right, so let's look at a case where we have a constrained optimization. We look at Lagrangians. Well, we'll look at this one next.